Hi everybody, this video covers section 3 of chapter 6, and in this section we are going to introduce to you the graph of the sine function and cosine function. First we're going to talk about periodic functions, and then we'll introduce the graph of the two functions. We will talk about some techniques associated with graphing. These really won't apply to you because in this course using MML you'll be required to recognize the graph and select it, not necessarily to produce the graph. Then we will also talk about how to look at a graph and come up with the equation associated with that graph, and we will do some applications with trig models, specifically with sine wave models and cosine models. Okay, so a periodic function. What is a periodic function? It is a function of the form f of x is equal to f of x plus np, which basically means that this value is going to repeat every np times, where n is an integer and p is some fixed number. That fixed number is called the period. Okay, and what does this function look like? Well, here's a periodic function. And let's take a look at it when f of x is equal to 0. Probably the most trivial point. When f of x is equal to 0, it's equal to 0. When f of x is equal to 0 plus 2, which is the period, times 1, it is still equal to 0. When f of x is equal to 0 plus the period 2 times 2, it is still equal to 0. And the same thing with 0 plus 2 times 3, and 2 times 4, or even 0 plus 2 times negative 1. And we could do the exact same thing with f of x equal to 1, same value, f of x, f evaluated at 1, f evaluated at 1 plus 2 times 1, or which is f of 3, or f of 5, which would be f evaluated at 1 plus 2 times 2, and so on. And as you can see, that the function basically repeats with a period. It repeats every 2 units because it actually has a period of 2. So, well, what about cosine and sine functions? Well, notice that the sine on the unit circle, the sine of s is equal to x, and the cosine of s is equal to y. And as you travel along the unit circle, s begins to increase. It comes back down to 0. It decreases, comes back up to 0. And as you spin around the unit circle, those values of x and those values of y continually repeat. As a consequence, sine and cosine are periodic functions, and the smallest value of p that makes this repeat is 2 pi, which makes that the period. As a consequence, it turns out that sine of x is equal to sine of x plus n 2 pi, and cosine of x is equal to cosine of x plus n times the period, which is 2 pi, for any integer n. So sine and cosine actually are indeed periodic functions. And this is the graph of the sine function. This I actually did in GeoGebra, but notice that it repeats that this is one period of the sine function, and it repeats every 2 pi. So its period is 2 pi. On top of that, you can notice that its domain is the entire real line. S can go on forever. S can be any value from negative infinity all the way to infinity. As a consequence, the domain is the real line. But notice that since we're on the unit circle, the range is always between -1 and 1, of course, including both -1 and 1. We can also see that this graph is continuous over the entire domain. And where is it across the x-axis? Well, it crosses the x-axis at -2 pi, -pi, 0 pi, and 2 pi, basically any integer of pi. What else can we say about this function? Well, here's the origin, and one of the things you can see is that it is symmetric about the origin. As a consequence, this is an odd function. The other thing that we can say is that the sign is related to the unit circle as follows. Notice that the argument consists of real numbers corresponding to either the angle length the angle length or the arc length, which basically is the exact same thing on the unit circle. And what is the output or the value? Well, in the case of sine, the value happens to be the y-coordinate. So the argument, once again, either the angle or the arc length associated with the angle, since they're the same, and the output or the value, of course, is basically the y-coordinate if you are on the unit circle. Okay, what about the cosine function? Well, once again, this is the cosine function, and notice that the cosine function is always equal to the x-coordinate. I actually should have had these be s and not x's. I probably need to fix that. So let's make this, since we're dealing with arc length, let's just call this s, and we'll call the argument s for lack of a better term. But once again, the domain is the entire real line. The range is limited between -1 and 1, with the -1 and 1 inclusive. It is continuous over the entire domain. The primary difference here are the x-intercepts. Now, the x-intercepts occur at the half pi angles. And how would you characterize that mathematically? We would say it is at every odd multiple of pi over 2. And the way you describe an odd number is you take n, multiply it by 2, you get your even number, or start off with the integer n, multiply it by 2, you have an even number. Add 1 to it, you have an odd number. So this is basically shows as every odd multiple of 2 pi. But once again, the period is the same. Now, unlike the sine function, the cosine function is symmetric to the y-axis. Notice here that cosine of x is going to be equal to cosine of negative x, so he has symmetry about the y-axis, and that makes this function an even function. And what else can we say about this? Well, the arguments of cosine, once again, consist of the real numbers corresponding to the angle measurements or the arc length on the unit circle. And then the value corresponds to, in this case, the x-coordinate. And one other thing that we want to notice about the cosine function is that the cosine function is basically a graph of the sine function shifted to the left. So let's see if we can take a look at that. Okay, well, here is the sine function. Well, actually, let's start off, and here is the cosine function. So the cosine function is the kind of transparent curve right here. You can see because it's equal to 1 when x is equal to 0, and then it goes on continually, and then it goes on accordingly. And here's the sine function. Now, what would happen if I shifted the sine function to the left by pi over 2? Now, that is the same as adding pi over 2 to the argument of the sine function. That's going to be sine plus pi divided by 2, and look what happens. They overlap. So that's what happens when I shift it by pi over 2. And if I take it away, or just to show it in a little way, here's pi over 4, so it's not shifted as much. And then here the sine wave is back to where it should be once I take care of this. And there we go. Okay, so that is an example that shows that the cosine function is a graph of the sine function, with the sine function being shifted to the left by pi over 2 units. Okay, and this gets us started with our first example. Here we want to graph this function. It is some number a times sine of theta. In this case, we want to graph 1/2 sine of x, and then we want to compare it to y equals sine of x. Okay, well here we create a little table, and we came up with 5 principal points in the area. Basically, they're all multiples of pi over 2. Okay, so when x is equal to 0, both sine and 1/2 sine is equal to 0. When x is equal to pi over 2, sine of x is equal to 1. 1/2 times sine of x, well, that's basically sine of x scaled by 1/2, so we get 1/2. Similarly, we have zeros at the pi's. We have at 3 pi over 2, we have -1 for sine x. That, of course, gets scaled to -1/2 or 1/2 sine x. And, of course, we have 0 and 0 at the 2 pi's. What does the graph look like? Well, there it is. This here is sine of x. This here is 1/2 sine of x. So it turns out that 1/2 sine of x is a vertical shrinking of sine of x. Furthermore, the graph of y equals a sine of x, when the absolute value of a is greater than 1, we have vertical stretching. When the absolute value of a is less than 1, we have vertical shrinking. What happens when a is actually a negative number? Let's go ahead and come back to GeoGebra and take a look at that. All right, so here I have sine of theta. This is sine of theta for the case where a is equal to 1. Once again, when a increases, we have vertical stretching. When a decreases, like here, we have vertical shrinking. Okay, so here we are stretching for large values of a, and we are shrinking for small values of a. What happens when a becomes negative? Well, then the equation flips. There we go. Here's a is equal to -1, and notice that the sine wave, instead of going up like it does in the base wave, actually goes down. Okay? And furthermore, then, as a gets smaller and smaller, it stretches even more. So once again, when a is large, we have vertical stretching. When a becomes closer to 0, we have vertical shrinking, and it gets flatter. And of course, when a becomes negative, everything flips. Now, the next thing we want to talk about is the amplitude. Consider y equals a cosine theta or y equals a sine theta. If this is the case, the range of both functions will be from negative a to a. However, the amplitude will always be the absolute value of a. So as a consequence, this function and this function, even though they're negative of each other, they have the exact same amplitude. The amplitude for both of these functions is 1 because they span from -1 to 1. Okay, so let's take a look at example number 2. And here we're looking at graphing sine of x, where we are going to scale the argument by some number, by some positive number b. And here we're going to graph sine of 1/2 x and compare it to y equals sine of x. Okay, so let's go ahead and do that. And we're going to look at this between 0 and 4 pi. So when x is 0, we have the sine of x is equal to 0, and sine of 1/2 x is 0. When pi over 2, well then x here is pi over 2, but 1/2 x is pi over 4. So sine of pi over 2 is 1, but sine of pi over 4 is root 2 over 2. When x is equal to pi, then sine of pi is 0, but sine of 1/2 pi is 1. And if we continue, we will have -1 root 2 over 2. Here they are both 0 because here we have pi, or we have 2 pi and then pi. Then we have 5 pi over 2, but 5 pi over 4, so that's negative root 2 over 2. Here we would have 0 because 3 pi is 0, but here we would have 3/2 pi, which is -1, and then finally root 2 over 2, negative root 2 over 2, and then finally 0. Both of them were 0 for 4 pi. What does that look like as a graph? Well, here is the base function, y equals sine of x. And here is y is equal to sine of 1/2 x. And notice that in this one, the graph of sine of 1/2 of x is stretched. It is actually stretched by, by 2. So sine of 1/2 x is a horizontal stretching of sine of x. Furthermore, if the graph of y equals sine ax, I probably should have been, so the graph of y of ax, if a is greater than 1, it's going to provide horizontal shrinking, but if a is less than 1, a in this case is always a positive number, we will have horizontal stretching. And we can actually see that in GeoGebra. So here is, let me put the a back to where I want it. That should, the amplitude back to 1, okay. And now I'm going to mess with b. Here we have b is equal to 1, but look what happens when I increase b. Then you actually see the sine wave is shrinking and shrinking and getting tighter and tighter, okay. But if I decrease b, something less than 1, then it begins to stretch. There it is, getting longer and longer and longer until it is almost flat. So here we have horizontal stretching for small values of b, and here we have horizontal shrinking for large values of b. Okay, now let's talk about the period of the sine wave and cosine. Notice that if we have if we have y equals sine of bx, or I'm sorry, if y equals cosine of bx or y equals sine of bx, we have that the period of both functions is 2 pi over b. And let's just go ahead and see if this makes sense. Let's go back to this particular problem right here. Okay, and notice here that the period of sine of 1/2 x is 4, or 4 pi. It takes a distance of 4 pi before the wave begins. And here the period of sine of x is just simply 2 pi. So our equation was that the period p is going to be equal to 2 pi over b. In this case, b is 1/2. So that's going to be equal to 2 pi divided by 1/2, which will be equal to 4 pi. So for this particular graph, it makes sense, and yes, indeed, it does make sense in general. Okay, so this brings us to example 3. Now, in this particular class, you will not, or this particular course, you will not be doing much plotting, but you will need to recognize plots, okay, or recognize the appropriate graph. And that's what we're going to be focusing on when we do these examples, because that's what you're going to have to do in your homework. So here, you're going to be asked to graph cosine of 1/2 x over a 2-period interval. Of course, you won't have to do it, but you do need to recognize it. First question is, what is the period of y equals cosine 1/2 x? Well, remember the period is going to be equal to 2 pi divided by b, and of course that will be 2 pi divided by 1/2, which will be equal to 4 pi. Okay, so that is our period. What is the amplitude? Well, there is no coefficient here, so that implies that a is equal to 1, so the amplitude is 1. We would have that a is equal to 1. And the last thing we need to do is choose the correct graph. Now notice that our period is 4 pi. So for 2 periods, for 2 periods, we need to go from negative 4 pi to pi. Now this one right here has a period of pi. This is out. It can't be it. Furthermore, it had this division is 2, so if it has an amplitude of 1, the cosine function should not go any higher than these two values. So this one definitely does not work. Now once again, this one does have the correct amplitude. If this is 2, then that's 1/2, and this is 1. So this is essentially 1 and negative 1, which is what we're looking for. But here we have a period of pi, and we're looking for a period of 4 pi. So this is out. This right here has a period of 4 pi. Okay? But notice that when x is equal to 1, x is equal to 0, we get a negative 1. Here, when x is equal to 0, we should be getting a positive 1. This is actually the graph of y is equal to negative cosine 1/2 x. So this one is out. So the only one that works is this one. How do we know? Well, first of all, it has the right shape. Since there is no negative value here, we don't have a flipping. Secondly, it has the period of 4 pi. That's one period. There's the second period. And thirdly, this value is 1. This value is negative 1. So the amplitude is correct. So there we go. Okay, let's take a look at another example. This one is the graph of y is equal to negative 5 sine 3x over a 2-interval period. The first question is, what is the period of y? Well, once again, b is equal to 2 pi, no, the period is equal to 2 pi divided by b. b is 3. So here, this is going to be equal to 2 over 3 times pi. And that's our period. What is the amplitude? Well, remember, the amplitude is the absolute value of a. Okay, well, a is negative 5, so the amplitude is going to be equal to 5. And thirdly, we need to choose the correct graph. Now, before we do that, let's actually look at this graph in GeoGebra. So here we are. Okay, now since this is negative 5 times sine of 3x, notice that when x crosses 0, we are going down instead of going up. So we actually have a graph that we actually have a sine wave that is basically flipped about the x-axis. So it's going to go down as x moves away from 0 and until it gets to -5, and it's going to go back up. So that's the kind of graph that we're looking for. So let's actually take a look at these. Now the first thing we want to remember is, one, like I mentioned before, the graph is going to be going down. This goes down after 0, as does this one. This does not. This must be wrong. Okay? The second thing we've noticed is that the period is 2/3 pi. This is one period that starts at 2/3 pi, as is this one. This thing starts at -6 pi squared, which makes no sense as far as the next coordinate is concerned. So this one has to be out. Okay? The third thing we notice is that the amplitude is equal to, the third thing that we notice is that the amplitude is equal to 5. So this graph should vary between 5 and -5. This graph varies between 1 and -1. This graph varies between, not -5, but 5 and -5. So this one must be out, and this is the graph that we would select. Okay, and for our last example in this class, we're going to look at the graph of y is equal to -3 times cosine of 6 pi x over a 2-period interval. The first question is, what's the period? Once again, the period is going to be equal to 2 pi divided by b. Well, in this case, b is equal to 6 pi, which is kind of interesting because the pi's are going to cancel. So we're going to have 2 pi divided by 6 pi, and that is equal to 1/3. Okay, so that's our period. And again, and then once again, our amplitude is going to be equal to the absolute value of a, which in this case is 3. So we are going to have a cosine wave with a period of 1/3, an amplitude of 3, and since we're dealing with a negative sign, it's going to be flipped, which will tell us that when x is equal to 0, y is going to be equal to -3, or y is going to be equal to -3 times cosine of 0. Well, cosine of 0 is 1, so y is equal to -3. So now we can come over here and select the appropriate graph. Now, once again, this is going to be over a 2-period limit, or over a 2-period interval. Notice for this one, we have from -1/3 to 0, and then from 0 to 1/3. So that is basically 2 periods. This one goes from -12 pi squared to 0, from 0 to 12 pi squared. So this is obviously wrong, so we can go ahead and X this one out. Okay, now these, once again, have the correct periods. However, this graph, the cosine wave ranges from -1 to 1. Okay, our amplitude, our cosine should range from -3 to 3. So once again, this is out. This one actually has the correct range. This is negative, this is 3, this is -3. But notice that y is equal to -3 cosine 6 pi x. So when x is equal to 0, y should be equal to -3. Here we have 0, 3. This is wrong. The only graph which is correct is this graph right here. Once again, here's our first period, 1/3. Here's our second period, 1/3. When x is equal, it looks like a cosine, but it is flipped as it should be since we have a negative a value, and when x is 0, we have that y is equal to -3. Okay, now for this one, here we have an equation of a graph. And we have a graph of a sine function or a cosine function. We want to determine the correct equation. Well, first thing we want to notice is that when x is equal to 0, y is equal to 5, or y is equal to 5 and it's at a peak. So this does not look like a sine function, but it looks more like a cosine function, not necessarily this cosine function. As a consequence, we know that we are dealing with a cosine function. So we have y is equal to a cosine bx. Furthermore, this thing varies between -5 and 5. When x is equal to 0, this thing is indeed equal to 0. So we know that we're dealing with y is equal to 5 times the cosine b times x. Now notice this. Now check this out. Here we start here, we go down, we go all the way up, and then this is where we begin to repeat. Okay, so this is one period of the wave. So the period is equal to pi over 2. Okay, and based upon the definition of the period, this has to be equal to 2 pi over b. All right. Well, if that's the case, then 2 over pi equals b over 2 pi. The pi's can cancel, and we have that 4 is equal to b. So our final equation is going to be that y is equal to 5 times cosine 4x. Now, once again, if this thing was flipped, then it would be -5 over cosine 4x. And now the last thing that I want to talk about in this particular class is basically interpreting sine wave models, or sine function models, or cosine function models. And here we have the average temperature in Phoenix, Arizona can be approximated by this particular function. Okay, where x is the month and x of 1 corresponds to January. So you know how the rest of them would go. So then according to this model, what is the average temperature during October? And once again, remember, since there's nothing specified, we must be operating in radians. And also, since we're dealing with a pi, chances are we are operating in radians. So we have that x is equal to 10. As a consequence, this means that we're going to have f of 10 is going to be equal to 19 times the sine of pi over 6 times 10 minus 4.3. And once you evaluate all that, we're going to add 74 to it. Now, if you knock that out in your calculator, you will come up with 76.97 degrees. And we want to round this to the nearest tenth of a degree, so this, since we have something greater than 5 in the hundredths place, this would round to 77.0 degrees. Okay, what about the last one? Well, we're looking at April. Well, for April, we have that x is equal to 4. So then f of 4 is going to be equal to 19 times the sine of pi over 6 times 4 minus 4.3 plus 74, and that will give us 71.02 degrees, which would approximate to 71.0 degrees. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.